Hi guys, in this video we're going to go over the scalar product, also known as the dot product. Given two vectors a and b, where a has components x1, y1 and b has components x2 and y2 respectively, we know that a dot b is going to be the product of the corresponding components. So we need to multiply x1 and x2 together, and we're going to add that to the product of y1 and y2. And that's the first definition of the scalar dot product. Let's just go over two examples. In the first example, we have a vector 2, 3, and we have another vector 5, negative 2. If we want to find the dot product between those two vectors, we multiply the corresponding components, which I have colored for you. So 2 times 5 is 10. And we have to add that to 3 times negative 2, which is negative 6, which means we have 10 take 6, which equals 4. In the second example, the dot product still applies to three-dimensional problems. So if we have a vector negative 1, 1, negative 2, and we find the dot product with 2, 6, and 3, what we're going to do is we're going to match up the negative 1 times 2 is negative 2. 1 times 6 is a positive 6, and 2 times a negative 3 is a negative 6. 6 take away 6 is 0, so we're just left with the negative 2. And that is the basic definition of the scalar dot product. The second definition that you may have seen before is where we have a dot b equals the modulus of a times the modulus of b times cos of theta. I'm first going to go over a proof of this result, and then we're going to talk about a few problems. So let's assume we have a vector A and a vector B, and we'll also have the angle between A and B. The way we prove this result is using the cosine rule, because we know that for the cosine rule we have a squared equals b squared plus c squared minus 2bc cos of theta. And it's that n at the bit there, that 2bc cos of theta, that is the hint that we have to use the cosine rule to prove this result. For this result, though, we actually need a triangle, so I'm going to fill in the blank there. So that blue line is vector b subtract vector a. So let's just put that a, b, and b take a into our cosine rule. What we end up with is the modulus of b take a squared equals the modulus of a squared plus the modulus of b squared minus 2 modulus of a modulus of b cos of theta. Now we're using the modulus there because the cosine rule is to do with lengths, not to do with vectors. Okay, so we're talking about the length of the vector BA, the length of vector B, and the length of A, and that's why we use the modulus brackets. We're just going to go on a tangent for a little bit, and it's going to prove an important result that helps us come to the conclusion. So assume I have a vector n, where n has an x component and a y component. We know that the modulus of n is the square root of x squared plus y squared, because that will give us the length of that vector using Pythagoras' theorem. And then if we square the modulus, if we square the square root, we end up with just what's inside the square root, which is x squared plus y squared. Now, another way we can write x squared plus y squared is the dot product of xy with xy, because x times x gives us our x squared, and y times y gives us our y squared. So if we find the dot product of xy and xy, we would get to the same result. And what do we notice? We notice that xy is actually the vector n. So that gives us n dot n. So the first result we need to help us prove the dot product, what we need to understand is that the square of the modulus of a vector is the same as the dot product between the vector and itself. And I've just left it at the top right hand corner over here so we can make reference to it. What we're going to do now is we're just going to focus on the left hand side. So we're going to focus on this b minus a, all squared. Now b minus a is a vector in its own right. From the previous result, we can write this b minus a squared as the dot product of b minus a with itself. And we're just using that result in the top right hand corner again to show this. Now, when we are finding the dot product of more than one vector inside the bracket, we just use the distributive law like we normally would, as if we were multiplying them. But again, we're not multiplying them, we're finding the dot product. So instead of putting a multiplier between them, we'll always put the dot product. So we've got our first times first, outside times outside, inside times inside, last times last, if you want to do the FOIL method there. And that gives you b dot b plus a dot a, and then we've got two lots of minus ba. So this is the result there. And now what I'm going to do is, again, this b dot b, I could write it as the modulus of b squared, using that result we proved before. And a dot a is the modulus of a squared. So the left-hand side essentially becomes all of this. So I'm going to plug in this into our original equation now. When I do that, we have the modulus of a squared plus the modulus of b squared minus 2a dot b, is that result there, equals, and the right-hand side and the side we didn't change. Now, you may notice that the modulus of a squared will cancel out, the modulus of b squared will cancel out, and what we're left with is a minus 2a dot b equals minus 2 modulus of a modulus of b cos of theta. And again, if we divide both sides by negative 2, those two will cancel out, and we are left with the result that we wanted, that the modulus, that the dot product of a dot b equals the modulus of a modulus of b cos of theta. This is quite an important result because it lets us do quite a few things with the vectors. Let's look at some questions now. We're going to go through 4 in total. The first one is, given a and b vectors, find the angle between a and b. And we're going to use the dot product rule above to help us solve that. So first of all, we need to figure out what a dot b is. So a dot b is going to equal 3 times 4 is 12, plus 2 times negative 3 is negative 6. And 12 take away 6 is 6. Then we need to find the modulus of vector A and the modulus of vector B. So the modulus of vector A is going to be the square root of 3 squared plus 2 squared. And that's going to give us the square root of 13. And the modulus of B is going to be the square root of 4 squared plus negative 3 squared. And that's going to give us 5. That's a 3, 4, 5 triangle. Now we're going to plug that into our equation there. So we've got 6 equals the modulus of A times the modulus of B times cos of theta. And we're going to divide both sides by root 13 times 5. So we end up with cos of theta equals 6 over 5 root 13. And that implies that the theta is going to equal cos inverse of 6 over 5 root 13. So what we're going to do now is we're just going to write that into the calculator. So I'm just in main. I'm going to go cos inverse, my bracket there, 6 over 5 root 13. And just make sure you're in decimal mode, because if you're not in decimal mode, it's actually going to give you the exact answer. So I'm just going to go like that. And the angle is 70.6 to 1 decimal place. So the required angle that we want is going to be 70.6 degrees correct to 1 decimal place. There is actually an easier way in the class pad to actually find the angle between these two vectors. All we have to do is we'll go to Math 2. We'll type in the two vectors as row vectors, so 3 and 2. So plug in 3 and 2. That'll be my first vector, and we've got the second vector is 4, negative 3. I'm going to go 4, negative 3, plug in that second vector. And then what we're going to do is we're going to go action. We're in vectors, so we're going to go to vector. And we want to find the angle between the two vectors. So we're going to go angle. And then all we're going to do is we're going to substitute in the first one, comma, put in the second vector, and when we hit equals, we get the same result, 70.6. If I wanted to find the modulus of the vector, so the length of the vector, that's called the norm of the vector. So that's the length of the vector there. So if we go find the norm of 3, 2, what we should end up with is root 13, which is what we got there. So again, in the class pad, it's going to be action, vector, and then you choose which one you want there. You can even find the dot product if you wanted to. So if you want to find the dot product between these two vectors here, I'll just copy all of that down there. And the dot product was 6, and that's the same result as we had for our dot product there. So it's all in action and vector, and you just decide which one you want to use. That's a good question 2 now. Question 2 is giving us two vectors, and they want us to find a take away b, the modulus of a minus b all squared. So there's two ways to do this. Now we've just learned the scalar product rule, so I'm going to do it that way first, and then I'm going to show you the second way after that. So what do we know? We know that a take away b all squared is going to be a take away b dot a take away b, and this is going to give us a dot a plus b dot b minus 2 lots of a dot b. Now a dot a is the modulus of a all squared, b dot b is the modulus of b all squared, and then we have to take away 2a dot b. So what do we need? We're going to have to find out the modulus of a all squared. Now we know what the modulus of a squared is because we worked out in the previous questions. That's going to be root 13 all squared. So root 13 squared is 13. We know that the modulus of b was 5, so 5 squared is 25. And we know that the dot product between a and b was 6. So 13 and 25 is 38. Take away 12, and this gives us 26. So the length of a take b all squared can give us 26. The second way to solve this problem is to actually work out what this new vector a minus b is going to be, and then we'll go through the same process. So vector a minus vector b is going to give us a vector, so a take away b is -1, 2 take away -3 is 5. And then we have to work out the modulus of a take away b, which is going to be the square root of 1 plus 25, which is root 26. So the modulus of a take away b all squared is going to be 26. So two different ways, but the first method I showed you, I did that one first because it's really important that you understand how these dot products, when you have the modulus of squared, work, because there's quite a few proofs we can use utilizing this idea here. But in an exam situation, there's nothing wrong if the vectors are simple enough to just find the resultant vector of a minus b, find the modulus of that, and then square it, because it can be a bit of a simpler process. Let's look at question 3 now. Given a is 2, 2, -1, and b is 5, -4, 2, show that a and b are perpendicular. Alright, so I'm just going to draw a picture here. What do we know about perpendicular lines? We know that the angle between perpendicular lines must be 90 degrees. So we know that the cos of the angle must be 90 degrees. And we know that cos of 90 is 0. So what that means is that a dot b is going to equal 0, because if this part of the equation is 0, 0 times the moduluses of a and b will also be 0. So if the dot product is 0, that's actually saying that the two vectors are perpendicular to each other. So what do we have to do now? We have to show that the dot product between a and b is 0. So let's set up the solution. So 2, 2, -1, dot 5, -4, 2. And again, we're going to multiply each of the components. So 2 times 5 is 10. 2 times -4 is -8. -1 times 2 is -2. Then take away 8, take away 2 is 0. Okay? Therefore, A and B are perpendicular. So here's the last question using the scalar product or the dot product. Calculate P, Q, and R given that A is this vector, B is this vector, C is this vector, and D is this vector. But we also know that B is parallel to A. We know that C and A are perpendicular, and we know that D and B are perpendicular. And again, because we know they're perpendicular, we know that the dot product between the two should equal 0. So let's just focus on B is parallel to A. Well, what do we know about parallel vectors? We know that they are scalar multiples of each other. So if we look at A and B, we know that A is 2, 3, 1. And we know that B is 4, 6, and B. Now what do we have to multiply vector A by? That's A and that's B. What do we have to multiply vector A by to get vector B? Well, we have to multiply it by a scalar factor of 2. 2 times 2 is 4. 2 times 3 is 6. And therefore we can work out what the value of P is now, because 2 times 1 should be 2. So from this result, we know that 2 times 1 is P, so we know that P equals 2. Because we know that vectors that are parallel are scalar multiples of each other. Next, let's look at C and A. So we know that if they are perpendicular, the dot product must equal 0. So let's do the dot product now. I'm just going to write it as a row vector form to save a bit of space here. So we're going to do C dot A. So 7Q negative 2 dot 2, 3, 1, 2, 3, 1, and that's got to equal 0. So 14 plus 3Q minus 2 equals 0. 3Q is going to equal negative 12, and therefore Q equals negative 4. So we've got our P, our Q, and now we just have to work out the R value. And we'll get that by finding the perpendicular using the dot product and making it equal to 0. So D dot B is going to be 3, negative 4R. So 3, negative 4R. Dot B is 4, 6, and 2, because we know what P is now. We know that P is 2. And we've got to make that equal to 0. So 3 times 4 is 12. Negative 4 times 6 is negative 24. And R times 2 is 2R. And that's all got to equal 0. 12 take away 24 is minus 12. So that means that 2R must equal 12 for that to equal 0. And R equals 6.